So what I want to talk about today is I want to talk about something called change of variables. And we're going to utilize change of variables when we can't use separation of variables or we can't utilize the integrating factor. So there are times in which a function is going to be not in the right form in order to use either one of those solution methods for the differential equation. So consequently, we'll utilize this change of variables. In order to use the change of variables, what I'm going to need is I'm going to need a function that is what we call homogeneous of degree 0. And there's a very specific definition of homogeneous of degree 0. We're not going to worry too much about it, but what we really want, how we know something is going to be homogeneous of degree 0, is if what we can do is we can algebraically, if we can change this function in such a way such that we can replace y over x terms with a v or v equals x over y terms, okay, with a v. And it just depends upon a particular situation as to whether or not we're going to use the v equals y over x or v equals x over y. If we can do either one of those things, then we do know that we have something that's homogeneous to degree 0. That's not the only time to have homogeneous to degree 0, but it's going to be the ones that we're going to be utilizing, and they're the most common times in which we're going to have that form of function. So I'm going to take this function that I have up here, x y prime plus y ln x equals y ln y, and what I'm going to do is I'm going to actually get a coefficient of 1 in front of the first term. So I'm going to end up with y prime plus y over x ln x equals y over x ln y. So when I look at this, the first thing that hops to my eye, okay, is this y over x term. And that automatically tells me that I might have something that's homogeneous of degree 0. Now, unfortunately, my ln of x and ln of y, they don't have y over x terms, and so I'm not going to be able to do my substitution yet, or my change of variable. So what I'm going to do, though, is I'm going to get my y prime all on one side, and I'm going to get my functions of x and y all on the other side. So y over x ln x, okay, negative y over x ln of x, plus y over x ln y, okay, and this is going to then just be y over x ln y minus y over x ln x. And one of the things that I can notice here is that if I factor out a y over x, I'm going to end up with ln y minus ln x, and that, utilizing rules of logarithms, is going to be y over x ln y over x. Okay? Now that I know that, what I can do is I can do this kind of change variable. I can change my y over x into a v. So this is going to then be v ln v. Okay? v ln v. And that's going to equal, well, dy dx. But that's a problem. The problem is that, notice we've got that y term in there, and I don't want a y term anymore. All I want is things that are in terms of v and things that are in terms of x. But what I do have is I have an equation. Okay? I know by my change of variable that v equals y over x. Okay? So that means that y equals vx, just utilizing some algebra. And then if I take the derivative, that's going to give me dy dx equals, and we're going to have to use implicit differentiation here, it's going to be dv dx, it's going to be x dv dx plus v, utilizing implicit differentiation. Notice that this is the derivative of v with respect to x times x, that function, and then it's v times the derivative of x with respect to x, which is just 1. Now we can just go in and substitute that. So I'm left with x dv dx equals, plus v, equals v ln v. Now, what we have here actually is kind of handy, because what it is we've now transformed this, kind of hairy function up here at top into something that is now a separation of variables problem. Okay, it may not be a tidy separation of variables, but it is separation of variables. So now I'm just going to do some algebra here. This is going to give me x dv dx equals v ln v minus v. Okay, and then that's going to be x dv equals v ln v minus v dx. And what you'll notice actually is that it turns out, because it's all, the change of variables is always going to kind of end up like this. We're always going to end up basically taking the inverse of both sides, the functions on both sides, okay? So this is now going to be dv over v ln v minus v equals dx over x. Now, with a little bit of algebra, you can actually see that this is going to then just be dv over v times ln v minus 1 equals dx over x. Well, now all I got to do is integrate both sides. It's separation of variables again. So we have dv over v times ln v minus 1 equals the integral of dx over x. Now, just to save us a little bit of time and to prevent myself from having to do hairy calculus, because I'd prefer not to, what I did was I utilized a computer algebra system in order to find the integral here. But it's not that hard. It's actually just a substitution. And then it's going to give me ln of ln v minus 1 equals ln x plus c. Okay? Now, in this case, although this is, in this case, what I'm going to do is I'm now going to solve for v, and then I'll solve for y. Back again. Sometimes you're not going to be able to do that. Sometimes what you're going to want to do is you're just going to solve for, you're just going to get to this step right here and then just substitute in y over x. Because sometimes it's just too hard. The algebra is just a mess. Again, you're going to use a computer system or something like that. And so you're best off not doing anything. But what we can do now is we can just go in and we can say, okay, well, I'm going to take this, I'm going to raise it to the e power, and that'll equal e ln x plus c. On this side, we're going to be left with ln of v minus 1, and that equals c x. Okay. Plus, okay, good. Cx. And then I'm just going to take e, I'm going to take it to the e power again. So e ln of v minus 1 equals e to the cx. And so this implies that v minus 1 equals e to the cx. And that gives me then that v is equal to e to the cx plus 1. Now what I need to do, right, because I don't really care about what v is, right, I want to know what y is. So consequently, I'm going to resubstitute y over x equals e to the cx plus 1, okay? And then that gives me that y, the solution to my differential equation, is going to equal is going to equal x e to the cx plus x. And that is my general solution. So, just to summarize, we start here, okay? We start with a function, and just like any other time with the function, what we're going to do is we're going to divide out the function that's in front of the y prime. So we left with this function right here. And what I want to see, or what I want to notice, is that either that I have a power of x, right, powers of x and y, or some kind of division of the powers of x and y, right, such that it might be homogeneous of degree 0. Okay, and in this case, that y over x kind of gives me is the big tip-off, the big giveaway. Then I'm going to do some algebra, right, such that I end up with a function that is in terms of y over x. Once I have that function, I'm then just going to substitute in my v's for the y over x. We can also utilize x over y, because sometimes that's going to be something that'll come out really easily too. Now, don't forget that you are going to have to account for this dy dx. We don't want y's. We only want v's and x's, okay? But we know that v equals something in terms of y and x. So, utilizing just some algebra, we get y in terms of v and x, and then that allows us to find dy dx in terms of v's and x's as well, okay? In this case, we end up with dy dx equals x dv dx plus v. If, on the other hand, you had v equals x over y, then you would end up with a different dy dx. Then we go back in, we substitute, and then I'm just working with separation of variables. I'm going to separate my variables into my v's and my x's, okay? My v's and my x's all the way down through here, okay? And then, finally, I integrate, like I would always do with separation of variables. And then I'm just going to go in and do some algebra in terms of, until I get in terms of what v is in terms of x, right? Just like I would do if I were like looking for y. But one last thing that I've got to do before I finish is that I'm going to have to substitute in y over x for v. I'm going to have to resubstitute in because I'm not concerned with what v is. I want to know what y is. And so consequently, I'm going to have to do that substitution. I do that substitution, and then I solve for y again. And then that gives me my answer. And that concludes how to utilize change of variables.